Well, hey there, I'm Dr. Tom Ulrich, and I like to talk about leadership and engineering, but also I like to talk about Arduino. Hey, you wish you had a shirt like this. At any rate, hey, in this video, what we're going to do is we're going to talk about DC brushed motors. And those are particularly, we're going to talk about the ones that came with your Arduino kit. So this lecture is going to be kind of a how do these things work? What are they? So by the time we're done here, I'm hoping you can answer these questions. What is a brushed DC motor? What are the underlying principles of physics for these things? How are they made? We want to make sure we have kind of a clear picture of what the insides are, and what kind of electric signals do we need to generate in order to drive these things. So first of all, let's take a look at the principles then. So what I've done here is I've said, well, I've taken some wire, I've wrapped it around a roll of masking tape, and what Ampere's law says, you know, if I flow current through a conductor, it's going to create a magnetic field. Now that's true whether the wire's straight or not, but in this case I did it all curly. And so then a kind of a question arises, okay, well, yeah, if that's the case, what is the direction of the magnetic field? Because one of the ideas of a brushed motor, of any electric motor, is we manipulate the electric fields in order to generate a torque. So we need to know which way is which. So what it comes down to is we use the right-hand rule. So we have to use a right hand. Now, when I was a freshman at UC Irvine, I was taking a physics class in which we had an exam, something to do with the right-hand rule. And I remember, in the panic of taking the exam, I'm writing with my right hand because I'm right-handed, and I thought, oh, hey, what a great convenience. I'll use my left hand for figuring out the direction of the vectors, and of course I lost a whole bunch of points because it doesn't work with your left hand. It gets all the polarities backwards. Any rate, so what you do then is if you put say you put 12 volts here and you put the ground there, this wire runs like this direction. So that means that the north is right here. The magnetic field is running in that direction. If we put the voltage over here, where now it's running this direction, you see now the magnetic field is in the opposite direction. The next principle we want to talk about is something called Lenz's law, and that's kind of an interesting one. What it says is if you move a conductor through a magnetic field, so let's say we've got a big MRI machine nearby, giant electric field, and you simply moved a conductor through the field, that will generate a voltage. Moreover, if you maybe you put a resistor between the two of these, or even if you just hook them together, moving this through the field will cause current to flow in these wires. So that's interesting. Let's put a pin on that. We're going to come back in about 15 slides to that. The other thing to know is when we talk about electric fields, when I said, hey, it's going this direction, the terminology we would say is that's the North Pole, that's the South Pole. And again, use the right-hand rule. Don't use the left-hand rule. You lose points. I know this for a fact. And a thing to know, too, is like if you have a coil, the pole is going to be orthogonal. Now, if you don't know that word, it means kind of like right angle in all the dimensions. So if the coil's like this, the vector for the magnetic field is going this way. If it's like this, it's that way. So the vector of the magnetic field is orthogonal to the coil. And the final little concept here is that opposites attract. So if you have a magnet, the north side of one magnet is going to attract the south side of another magnet. Conversely, the south side of a magnet attracts the north side of a different magnet. If you take two norths together, if you've ever had two strong magnets and tried to push the norths together, they push you apart when it's north repels north, south repels south, and the stating the obvious, then physical forces result from how you manipulate these fields. You get a north and a south, and it's a physical force pulling it together, and you go north on north, that's a physical force pulling it apart, and that's how we create force, or in the case of rotary equipment, we create torque. All right, so what is a brushed motor? Well, first of all, let's look what's in your Arduino kit. So you'll see, if you root around there, you'll find there's a motor and a fan that come together. That's a brushed motor. If you look on your little Arduino kits here, these are brushed motors. You'll see there's a stepper motor in your kit, not a brushed motor. You'll see there's a servo motor, not a brushed motor. At any rate, so here's kind of the principle. So it kind of goes like this. There's an outer piece and an inner piece, and the inner piece spins and the outer piece doesn't spin. So the outer piece is called the stator, and the stator pretty much is comprised of permanent magnets. So, you know, some material's magnetic. Those are called permanent magnets. You have two of them. Notice that in the picture here, we've got the south side of the top magnet is closest to the rotor. The north side of the bottom magnet is closer to the rotor. This won't work if you have, for instance, if the south side of both magnets is closer to the rotor, this won't work. They have to be opposite. Then the rotor is the part that spins, and what it is are electromagnets. Now, you may not know this, but I kind of demonstrated it here. You know, if you take a coil of wire and you run a current through it, that is a magnet. So when I say it created a magnetic field, what I'm saying is it is a magnet. So when you get a magnetic effect by running a current through something, that's called an electromagnet. So the stator has permanent magnets, the rotor has electric magnets, and the whole deal is we're going to manipulate the voltage on the electromagnets to manipulate the magnetic fields to get it to spin. All right, and what's important to notice is how these are wound. A lot of times you'll see magnets where they're sort of wound this way, but to make a brushed motor, you have to spin them this way. So this would be the rotor. Now this is just a piece of PVC pipe, and this is just string, but you know, it communicates the point that with a brushed motor, you wrap the wires this way. See that there in all these different dimensions? Okay, so that's physically what is a brushed DC motor. And now a very legitimate question here is, so why am I saying they're brushed? What are we talking about? And you know, the answer is we say they're brushed because there's brushes. Now these are paintbrushes. I use them for painting model airplanes, but it's the same concept. Suppose we had these where this was conductive and these little hairs were conductive. Those are brushes. So, you know, the whole key to a brushed motor is that when they make them, they have a system of brushes and brush pads. And the idea is, you know, if there's a voltage here and I touch it to my hand, I am now shocking myself, right? So the pad and the brush, and that's the fundamental piece here. Now, when you do this, when you have brushes and brush pads, that's called the commutator. The process is called commutation. So it's the commutation process of a brushed motor. Now, why do we do this? Well, let's think about that for a second. So let's suppose we have this conductor. That's good. So we hook a wire here and hook a wire there. But now this is on the inside, so it spins. You know, it's going to reel in whatever wires are connected, kind of like a fishing line reeling up, you know, the fishing line, or the fishing pole reeling up a fishing line, right? As the motor spins, we can't have the spinning motor like pulling on all the wires, so we need this system of this commutation system. And the other thing is we also need this system to allow us to change which pin. So what we find is we use a brushed motor is, you know, maybe we start off by having 5 volts here and a ground there, but as it spins, what we discover is we have to, instead of having the 5 volts here, we want the 5 volts there, and we want to have the ground there. So we need a system that can dynamically change where the voltage is being applied, so that so we can appropriately manipulate the magnetic field to get the most torque out of the motor. All right, so what do these look like? Well, you know, in my little PVC thing here, I don't know how well you can see that. But what I've done is I've connected the little orange string to the green pad on this side and to the orange pad on this side. And then what I do too is I took one of these things for holding pieces when you solder them together, and that's what you're seeing in the picture here. So I kind of created the pads with that. And the whole idea is that by having the brushes and the pads, is as it turns, it flips which brush is contacted with which pad. And what that does is that it affects flips of which side of the coil we're putting the 5 volts here or putting the 5 volts there. Now, in terms of this system, brushes and pads, I mean, this system makes it so brush motors, as a rule, are much less expensive than alternatives. The brushless motors, brushless DC motors, kind of the opposite. Those are they're more expensive because what you need is you need to have something where you can sense the angle of the rotor, and then you need a bunch of circuitry to drive it. And so actually the motor itself for brushless is a little bit less expensive to build, but the circuitry and the cost of the sensors make it where it's much more expensive to use brushless. The downside of brushless, if you think about it, is they will wear out because you've got this brush, this motor spinning, and eventually the brushes wear out. It also tends to arc, so as it goes from touching to not touching to touching, you'll see little sparks. And if you've ever had like an electric train set or a little electric car, sometimes if you're looking or if it's running in a dark room, you're like, hey, it's sparking in there. Well, yeah, that's the brushes and the pads making and losing contact. Having said that, you can get brushed motors that are sealed to keep the arcs in. The other thing, as we'll see, is the gaps can cause some trouble in terms of controlling. So we'll get to that. All right, so what makes these motors spin? Well, let's take a look at the physics here. So in this slide, first one I'm trying to show is, okay, let's suppose the angle's not changing, so the motor is still for the moment. And all we're doing is changing where we put the 5 volts. So on the left, we put 5 volts on the little wires. So that'd be like we put the 5 volts here and put the 0 here. And what you see is it'll go the direction in this one on the left, which you'll notice is the North Pole is kind of near the north side of the bottom magnet. And so that's going to repel. And so that's going to push it in the clockwise direction. If you don't know that terminology, that was before digital clocks. It used to be all the clocks kind of had 1, 2, 3, 4, 5, 6, and so on. And so clockwise means it's like going from 1 to 2 to 3. So clockwise is the way a clock normally goes, the way a second hand spins. Counterclockwise is the opposite. At any rate, the one on the right, you see how I flipped where the 5 volts is, and what you'll notice there is now the South Pole is near the bottom magnet's North Pole, and so that's going to pull it toward it. So the one on the left, the bottom is pushing it away, and on the right, the bottom's pulling it. And if you'll notice, at the same time on the left, not only is the bottom magnet pushing away the North Pole, the top magnet is pushing away the South Pole. So both ends are contributing. And then on the one on the right, it's the converse. On the bottom, that north magnet's pulling in the South Pole, and on the top, that south magnet is pulling in the North Pole. All right, so now instead of having the angle fixed and changing the voltage, let's change the angle. So on the left, what you see is it's pretty much the same as what we just looked at. So on the left is the bottom north is pushing away the rotor's north, and the top south is pushing away the rotor south. But as the motor continues to spin, what you'll see eventually it gets to the point where now it's in the next picture it's rotated 90 degrees, and so what you see is the top south is pulling in the north and the bottom north is pulling in the south. And so in both of these ones we've got the voltage on the little wires that have the white font. So you see there I've got some wires with white font and some wires with black font. And any rate, so for half of the time, we want the 5 volts going to pin 1 of the first wire of the white, and the ground going to the pin 5 of the dark font. But there gets to be a point at which it goes past the half point, where now look what happens is we put the 5 volts on the black fonted ones and the 0 on the white. And so the 5 volts goes to pin 5 of the black and 0 goes to pin, and notice what's happening then. So, you know, if you use your right hand rule, right, where the voltage is that's where, you know, think of it as the wires are going into the page, and so you kind of reach your fingers in and you see that, oh, yeah, that as it goes down to the pin, that's where the north is. And then on the one on the right, you can kind of do the same thing. So you can see how the north is manipulated. But the important thing is, you know, it's kind of the, you can see that we had to switch putting the 5 volts from the white fonted wires to the black fonted wires. And so that's how the commutator's doing then is, you know, half the time it's wired up so that the 5 volt brush is touching the green, and half the time it's wired up so the 5 voltage is touching the orange, and that's how it commutates. Now, there's one thing to know here is there is this phenomena of stall. Right? So what you see here is in this case, it's not clear which way it should go because, you know, the north is near the south is near the north. It doesn't really want to go anywhere. So you have this thing where when you're perfectly aligned with the poles, you can stall, and the solution there is you add more poles. So this one had 2 poles. If you had more poles, then you can avoid that. And the other one is you have this phenomena that, you know, if the motor stopped right when the brush was in between, right? So it's spinning, and then you stop the motor and you go to restart it, like, oh, it's not touching the green, it's not touching the orange, what do I do? And that's a challenge. And you know, you say, well, what's so hard about making a DC brush motor? Well, that's pretty much it right there, is how do you do the commutator so you don't have these stall points. In general, you know, if you look at the torque generated by these motors, it's not like there's a flat, you know, it's not like it's flat. It tends to be, you know, there are points where it's lower than others because of all these sort of phenomena. All right, so let's say that I mentioned briefly we can add poles, and what we can do is here's another picture of the PVC pipe where I just put I have some white string and some gold string, so now I've got 4 poles instead of 2. And you can kind of see the zoom here. So now what I've done is I've shown the white wires as like green and the yellow wires as this brownish color. And what you can see here then is you can kind of alternate between which set of coils you're energizing. Now that'll totally solve the stall problem where, you know, it's aligned funny. You still have some fun with getting the gaps between the commutators. But so in this picture, what we do is we are energizing the wires that are shown there as brown. And then in the next picture, you see now we're energizing the wires shown in green. And the one thing to note between both these pictures is in both cases, in these 2 pictures, they were both going counterclockwise. And they were both, so in the first one, we had the 5 volts on the dark font for the brown, and on the second one, we had the 5 volts on the dark font for the green. Anyway, so you can start to imagine in your mind, okay, we could have 8 poles or 12 poles or 6 poles or 24 or whatnot. And you can start to imagine in your mind like how you can solve. And the more poles you tend to make the bouncy, you tend to even that out a little bit. All right, so the final question then is how in the world do I drive these things? What kind of signal? Now the good news is you just pretty much slap a voltage on it. So here it is. Motor coils have resistance, and when you apply a voltage, Ohm's law dictates there'll be a current proportional to the voltage, V equals IR, right? And another thing to know is torque generated by a motor is proportional to the current. So if you have a current, you get a torque. And of course, Newton's law, torque causes acceleration. So if you have a torque on a rotary machine, it's going to accelerate. All right, so that seems pretty straightforward in physics, right? So let's do this little thought experiment. So let's suppose the coil resistance is constant. It's not heating up, it's not changing, it's just constant. Let's suppose there's no friction, so somehow we came up with a scheme of perfect bearings, and let's suppose there's no drag, so we're doing it in a vacuum or something. So the question is, will applying a fixed voltage cause the motor to accelerate infinitely? Right? Because the voltage creates a current, the current creates a torque, the torque creates an acceleration, the acceleration makes it increase in velocity. So will applying a voltage cause this thing to go on forever? Well, the answer, hopefully, the answer is no. But let's learn why. So remember I said let's put a pin in the idea of Lenz's law. So that's a really interesting thing here. So remember, if you're moving a conductor through a magnetic field, it creates a voltage. Well, have you got a magnetic field? Well, yeah, you see we got these two permanent magnets. See, they create a magnetic field. And are you moving the conductor? Oh, well, yeah, you know, the thing, it's spinning. So, yeah, it's definitely moving. Okay, so you've got a conductor going through a magnetic field. Yeah, I don't know where this is going here, Tom. I'm not sure I like that. And I definitely do not like that shirt. Okay, so let's look at it here. Let's look at a very specific example. So let's suppose the coil resistance is 10 ohms. Let's suppose the applied voltage is 10 volts. So using Ohm's law, you have 1 amp. So the 1 amp creates proportional amount of torque. The motor starts to accelerate. Now you have a conductor moving through a magnetic field, and Lenz's law kicks in, and it starts to create a voltage. But here's the thing, we call it a back EMF because if you look at Lenz's law, there's a negative sign. The voltage is like in the opposite direction, so it like eats away from that 10 volts. So let's suppose the rotation gets to a speed where now there's 1 volt of back EMF. Okay, let's revise our calculation. The coil resistance is still 10 ohms. Now the net voltage is 10 minus 1 because the back EMF is sort of subtracting, you know, it's sort of opposite the voltage you apply. So now you've only got 9 volts available to generate the current in the coil. So now the current is 0.9 amps instead of 1 amp. So the motor continues to accelerate, but it's accelerating at a lower rate because the current's lower. And now, but the motor's still going, and now it's even going faster. So it's accelerating at a lower rate, but it's still going faster than it was initially. So now let's say the back EMF is 2 volts. Okay, well, now you got the back EMF is 2, you're applying 10, that's 8 volts of net. The current now is 0.8 amps. And you see now the motor's continuing to accelerate, but less so because the current. And so then it's still going faster, and now you got 3 volts of back EMF, and you see how that goes? And then it keeps going, but now you've got 4 volts in there. And eventually what happens is the back EMF continues to raise until it equals the applied voltage. So if you apply 10 volts to the motor, it will accelerate until the back EMF is 10 volts, in which case it'll accelerate no longer. So even if you have no friction, no air resistance, perfect coil, all these things with an electric motor, for each voltage applied, there is a corresponding speed, maximum speed. Now, you'll notice also that the premise here is, you know, as the voltage, the back EMF hits the applied voltage, now there's no torque to further, you know, no current to create torque, so it doesn't further accelerate. But notice then there's no torque, which means if you're going at your maximum speed and then you put a load on it, so you try to drive a belt or something, you'll see it will slow down because it needs some current to generate the torque. And so what it is speed control is kind of a, there'll always be a correlation between voltage and speed, but as you have a load on the motor, that a maximum voltage will actually change. Any rate, so bottom line here is voltage level determines the motor speed. So when you're using your Arduino, it's very simple. You're going to use a digital output. You're going to set it to PWM, so you got to use one of the ones with a little tilde on it. That means PWM. And as you write a different higher or lower PWM value to the pin, the motor will go faster or slower. All right, so in summary, DC brush motors are inexpensive and they're simple to use, so that's kind of the good side. Now on the bottom, or the negative, the problem with brush motors is they can have shorter lives. The simple reason that the brushes wear out. They tend to arc. You do not want to use a regular DC brushed motor in like near oxygen. So let's say you're in a hospital environment and you're going to make a ventilator. You don't want to use the kind of cheap little motor that came with your Arduino kit. You don't want to use it near oxygen. That can go boom. You don't want to use it like in a chemical plant where they're making turpentine or something. That can go boom. There are versions available that are sealed for arcs so that the arcs sort of stay inside. There are versions available so the brushes last longer. In fact, there's a picture there of Tandem Diabetes Care T-Slim X2 with Control IQ algorithm. When we made that, we use a DC brushed motor. We just use a medical grade one so it doesn't arc. The brushes don't wear out over the 4-year period and so on. But for the motors that came in your Arduino kit, do not use those around oxygen. Do not use those around volatile chemicals or liquids. I mean, basically you got to be aware that those things will wear out and they will arc. Hey, at any rate, that's all I got to say about DC brushed motors. If you like this video, if you don't mind giving it a little like, if you subscribe, that'd be great. YouTube recommends me to more people as I get more likes and subscribes. If you want to see more videos on either Arduino or on how to lead engineers, go to my website, tomulrichconsulting.com. If you're on YouTube, you can just search on Dr. Tom Ulrich. That seems to work. At any rate, thanks for listening, and we'll talk to you later.